I really need to pick a starting catchphrase or something for all these videos I do. Anyway, I want to do this. Center of mass for the Earth-Moon system. You ready? Okay, so here's the Earth over there on the left. It's a big ball. And then over on the right, a little bit in the middle of the page there, we have the moon. And then there's the distance. Now the distance is from the center of mass of one object to the center of mass of the other object, because it's really the center of masses, right, that matters. Everything else we don't really care about. So here we go. We've got the radius from the center of the Earth to the moon, and of course the moon goes around the Earth. And so that's why we're doing it this way. So anyway, the radius of the Earth-Moon system, the distance between those two objects, is 3.82 times 10 to the 8 meters. And just because we're going to be using it later, the mass of the Earth is 5.98 times 10 to the 24 kilograms, and the mass of the moon is 7.36 times 10 to the 22 kilograms. And the moon is a lot smaller than the Earth, but look, it's only a factor of 100 times less massive. And when you're dealing with 10 to the 22 or 10 to the 24, you might think, oh, wow, man, that really doesn't matter a whole bunch. But that difference is quite a lot. 10 to the 24 versus 10 to the 22 is a lot. That's 100 times more. And it equates to the gravity on the moon as being about 1/6 the gravity on Earth. And if it get too small, well, the moon's actually too small, it can't have enough gravity to maintain a atmosphere, which we need to live. So anyway, okay, I just wanted to throw that out to you guys, a little info about the Earth and the moon and all that. Okay, so we drew a diagram of this system. Okay, so that's the first thing that we did. The second thing is we're going to assign our coordinate system. So we're doing a little coordinate system work. So here's our coordinate system. And we've decided that the center of the Earth is our origin. I've labeled the radius of the Earth here just so we can see it. And then over here, I'm going to drop down. This is the distance, radius, Earth, moon. That's the distance to the moon from the center. And I just got a buzz on my watch. I don't know why. Okay. So equation for the center of mass, we did this in class. I'm not happy with how we derived it, but at any rate, we did derive it. And so we've got the radius of the center of mass. We've got 1 over the total mass of the system. Okay, so I wrote a big M here. And in fact, this big M, if you want to think of it in terms of all the little m's added together, it's the sum of all the little m's. Okay, so we add up all the little m's and we turn that into the big M. And then we have another sum where we take all the little m's times their radius, the point away from the origin, which we define. Okay, we define the coordinates. So we're going to define relative to our origin where the center of mass is. Okay, so that's up to us. All right, we could go halfway. We could say this is our origin and then define from there. All right, a little more difficult to do. Choosing one or the other is easier, and one or the other objects, when you have two, that'll be easier, and you'll see why in a second. Okay, so we've done those two things. We wrote down our equation that we're going to work with. Okay, I've got it, big box there full of equation. And we're now going to just kind of do a little math. I didn't write down the math part, but we're going to do a little math. So I'm going to rewrite that RCM as R center of mass is equal to the sum. So I'm essentially taking the numerator and I'm making it the sum of all the bodies times their respective radius away from the origin. And then we're going to add up all the bodies. So where's the... Let's do it. This bit goes down here, and that top one goes up there. Okay? That's it. Now, if we look at our RCM for our system, essentially what we're doing is we're taking the mass of the Earth times the radius to the Earth from our origin. This isn't the radius of the Earth, okay? It's from our origin, so to the Earth. Then we have the mass of the Moon times the radius to the Moon on our origin. And then the total mass of the system, which would be the mass of the Earth plus the mass of the Moon. So let's write out those things. And since our origin and where the Earth is are the same, the radius of our Earth distance from the origin to the center of our Earth is 0. Okay, so that whole term goes away. So now we're just left with the mass of the Moon on top. And so let me write down the mass of the Moon times 10 to the 22 kilograms. And then we're going to multiply that by, from our origin to the Moon is the radius Earth-Moon distance. And that's 3.82 times 10 to the 8 meters. And then we're going to divide all that out by our mass of the Earth, 5.98 times 10 to the 24. We can keep these guys. And we're going to add that to 7.36 times 10 to the 22 kilograms. Anyway, you'll notice that these kilograms and all these kilograms cancel out, and we're going to end up with nothing but meters. And what does that actually equal? That's 4.64 times 10 to the 6 meters. Okay? So let's move up here. Let's give ourselves some room. Our R center of mass from the origin is equal to 4.64 times 10 to the 6 meters. Okay, there's our answer. We're boxing it in. We've sealed our fate. So let's go back up to our picture. And I just want to note one thing. The radius of the Earth. So let's write down what the radius of the Earth is. Radius Earth. That's equal to 6.37 times 10 to the 6 meters. Okay, so that's this distance right here. Okay, 6.37 times 10 to the 6. That's that. What did we come up with? We came up with 4.64 times 10 to the 6. Oh boy. So the center of mass for the Earth-Moon system is just a little bit less, 2 times 10 to the 6 meters. So we got to go below the surface. It's not at the actual Earth, but just below the surface of the Earth is our center of mass for the system. So let's look at that in a new way. So here's I love blue, so and I love the Earth. The Earth is blue. There's the center of mass of the Earth. Well, let's do green for the center of mass of the moon. And we'll do black because it's so official for the center of mass of our total center of mass for our system. Okay? So we have found the center of mass for our system for these two objects. Now, the moon, let's say, goes this direction around the Earth. Well, they both have to circle this center of mass, okay? So if that moon is going that direction, then the Earth is going this direction, and the Earth goes in a circle about the center of mass like that, and so does the moon. Okay, so they both go about this center of mass. Okay, they both revolve around that center of mass, and they revolve around that center of mass in the same time every day, or whatever. What is it? Once a month, 28 days, something like that. They both do their revolutions about that point. Well, it turns out that that point is bigger. I'm sorry, the distance from the center of mass of the Earth to the center of mass of the system is smaller than the actual center of... That was terrible. Let's try that again. All right, there we go. The center of mass of the Earth is there, but the radius of the Earth, the extent of the Earth, goes all the way out to here, right? That's the radius of the Earth. So it's it's inside the radius of the Earth. So what does the Earth do? The Earth just kind of wobbles, right, around that center of mass due to the moon doing its thing. So the Earth kind of, it wobbles around. They both rotate, okay, about that center of mass. Okay, so what about... That's a pretty simple situation. Planetary and orbital motion. Well, it's simple as long as you have two bodies. Okay, two bodies, simple. Three bodies, and there's a complicated. So when you say, oh, my relationship is complicated, it means you're probably not dealing with just two bodies. You're dealing with three bodies. I'm just kidding. Okay. There's a show coming out, and I don't know how much science or whatever is involved with this show, but it's called the three-body problem, and it probably has more to do with... dating and romance than it actually has to do with physics and stuff. That's fine. But the three-body problem is a famous problem in physics, and it involves when you have bodies that are in a system, this one, and they're all rotating around some center of mass. Okay, they're all going around our center of mass here, COM. So, yeah, the three-body problem and how to manage their movements, you can look into it, but technically, young people go, oh, I can solve that three-body problem. And then you realize that you can't, because life is chaotic and chaos is unknown, right? So anyway, you just, I don't know, get Buddhist or something and realize that some things are not doable. That's one of them. So, we're going to do, for extended bodies, extended objects, the center of mass. So, extended object, what am I talking about? It could be some object like this, and I don't know, it's 3D, so it's full of mass, matter, whatever. And for whatever reason, we want to find the center of mass of this thing. Okay, so we want the center of mass. Okay, for that thing. Okay, so let's look at our RCM, and of course that's, we can write it out like this. So we're going to go from J equals 1, MJ, RJ, and we're going to divide by J equals 1 to N of MJ. Okay. All right. So that's our center of mass. Let's do 1 over M times our sum MJRJ. Okay. I want to do it this way because this is just our total mass in the denominator. So let's just leave it as our total mass, all right? Because we could take this object and stick it on a scale. We'll take this object here, we'll put it on our handy scale and measure it, right? So there are ways. We have ways. All right, so fine. If we want to, instead of taking a hunk out of this thing, so we could take some hunk right here in the bottom, we take that piece, and then we have to piece all the J number of pieces together. Instead of doing that, okay, we're going to take our little MJ pieces and we're going to turn them into DM, okay, smaller pieces. So our sum isn't going to be over these MJs, it'll be over the DM, which is an infinitesimal mass, right? So you guys get it. I'm not going to write out infinitesimal mass. It's very small, right? So what does that mean for our RCM? We're going to do 1 over the mass of the object, total mass of the object. We're going to do the integral of all of the different R's, and here's what we do. We define a coordinate system where there's our origin. Okay, we define that coordinate system, and then all those points, we're going to do an integral over the whole mass. Okay, so we're going to do an integral over the whole mass, meaning we have now taken this part, turned it into dm, and then this would be the distance to each of those little dm sections. And this is how you would find that. Okay, so we need to do an example. This example is straight out of the book, so you can go in the book and look at it. This is the thin loop example. The thin loop. Let's see, 9.18 in the book. All right, a thin loop. Oh boy, here comes my sweet, sweet drawing. All right, there's our thin loop. We're going to select a nice spot right in the center of that thin loop as our origin. And the nice part about this is our radius is going to stay constant. So that guy ends up being a constant, which is pretty nice. Makes things a little bit easier. And we're going to cut up into little dm's all around the loop. Okay? So what is the mass for dm? Okay, so lambda is the mass per length. Okay, mass per length. Okay, so our material, however thick it is, whatever, lambda is a property of that material. And if we want to write it out, then dm is going to be equal to lambda times ds around the circle. Okay, so we've got some subtended s. So let's think about this. From here to there is some distance s, and we want just the part of s that equals this dm. So that would be ds. All right, so that's the distance. So we multiply this lambda times that distance, we get the mass. So good. Now, lambda is equal to the total mass of the object. So let's call it total mass of our object. And we're going to divide that by 2 pi r. Why? Because that is the distance all the way around the circle. So okay. Okay, I had to unplug my computer. Okay, so good. Now, ds. Let's deal with that for a second. ds can be at any point. All right, so, or it has to be at every point. And we kind of want to do a thing where we do x and y. All right, so in our situation, we can say that x equals r cosine of theta, and y equals r sine of theta. Okay, you guys with me so far? So we're going to take that and we're going to end up saying, okay, we've got ds is equal to rd theta, which means dm is equal to lambda rd theta. And we know what lambda is, so let's put lambda in there. So we've got our total mass times r. We're going to divide by 2 pi r. And we're going to multiply that by d theta. Okay, so now what have we done? We have gone like this. And we said that this little angle in between that makes up our dm is our d theta. Okay? All right. Well, that ends up giving us the r's cancel. So we end up with big M over 2 pi and then d theta. That's our dm. Okay, so we can now start working with our equation that we have up top, boxed in there. Follow me. RCM equals 1 over Rm. Okay, but we're going to do the integral. Now, we have two different directions. We have this in the I hat direction and this in the j hat direction. So we're going to say r cosine theta I hat, let's put a little I hat on there, plus r sine theta in the j hat direction. And we're going to put a little dm on there. Okay, so that's our first step. All right. We have taken r and we've busted it up into the x and y's. Okay. Now, we're going to do it again, only this time on the inside of the integral, I'm going to put 1 over m. And then we're going to do all of our r cosine theta I hat plus r sine theta j hat. And instead of dm, I'm going to write capital M over 2 pi d theta. If you notice, this m and this m are going to cancel. And out front, we can stick our 1 over 2 pi because that's not going to, that's just a constant. So RCM then is going to equal 1 over 2 pi times the integral from 0 to 2 pi r cosine theta in the I hat direction plus r sine theta in the j hat direction, j hat, and all of that d theta. All right, so far so good. RCM 1 over 2 pi. Now here's, we can't do each of these integral, we can't do the integral together. We need to do this integral and we need to do that integral and then add those two things together. All right, so that's what we're going to do. We're going to go 0 to 2 pi r cosine theta d theta. We're going to do that in the I hat direction. And then we're going to add to that the integral 2 pi our sine theta in the j hat direction. All right. Good. You guys should stop right now, pause this video, do those integrals, okay? Or not, of course. You don't have to, but you're going to notice one thing, hopefully, and that is we've got 1 over 2 pi. We're going to multiply by this integral. When you do this integral, 1 over 2, from 0 to 2 pi, you're going to find that that all equals 0. Okay? Better than that, you're going to find that all of this integral also equals 0. So, what have we just said? The radius of the center of mass is equal to 0 I hat plus 0 j hat. Okay, now let's go back and look at our picture. We defined the center, our origin, to be this point right here. Our origin is the center of mass. We defined it to be that way, and when we're done, we find that it's exactly where we chose the origin to be, is our center of mass. So I hope you guys understand that and are able, you know where the hard part is? Okay, I know where the hard part is. It's up in here. Whoa. This right here, that's a hard part. This over here is also a hard part. So it's figuring out how to get our d thetas or other things from our dm. That is really, that's where the thought goes in. And a lot of the work was done right here for us to get to that point where we have 0, 0. So go back through, look at that example, make sure that you know how to and understand how they got what they got. And if you need to talk about it more, we can do that. So, good. Now, there's an easy way to do the center of mass. Everybody wants the easy way. So, center of mass, the easy way. Why didn't you tell us the easy way right off the bat? Well, it's not the easy wa, it's the easy way. I don't know. I don't know why I didn't tell you right off the bat, but let's say we have an object. Okay, we've got some object. I don't know. It's this long, and it has an extended body, but it's all in the x-axis, and we can cut it up into little sections. If we're going to do it, if you're going to cut it up into little sections, you want to cut it up into equal sections, okay? Each of those sections has a center of mass. And then you pick an origin. So we could say this is our origin. We could also define our coordinate system. X goes that direction. Here's X. And we want to know what is the center of mass for this object. It doesn't matter. So we want center of mass for the object. We're going to take m1 times this distance. Okay, that's x1. And we're going to do m1 x1 plus m2 x2 plus m3 x3 plus dot 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 all the way to, ooh, I did a plus, a times sign, but I want a plus sign. And we're going to go all the way to m, what do we want? We want n of them, xn, okay, all the way out to there, and then we're going to sum up m1 plus m2 plus dot 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 all the way to mn on the bottom. So that's the total mass of the object. And xn here. All right. So good. But what did we just do? We just said xcm is equal to the mj xj, and we divided it by j equals 1 to n mj. And of course the bottom is just the total mass of the object, and then that means we're left with j equals 1 to n mj xj. And all of that would be, of course, in the I hat direction, and you can do it in 3D if you want. You can do I, j, and k, and when you do, you get your RCM is equal to our sum from j equals 1 to n mj rj. And that is it, guys. So there you have it for the center of mass of an object. Maybe look at some examples if you need to. Go over it a couple of times with problems in the homework on web work and in the book. And you should be golden. Thanks for your time and attention and paying attention and all that.